let's talk about how to find the derivative as well as how to integrate functions involving exponentials and logarithmics. All right, now, I know we keep saying it's just algebra. If you need to review the definitions of logarithms and exponentials, and this is basically a copy-paste of my college algebra notes. And so, this is just a very quick breeze through of the relationships that you would have learned in a college algebra class. Very quick. But we have exponential form and we have logarithmic form. And that was a pattern that we practiced extensively. Fortunately for us in calculus, you don't have to necessarily have to understand these patterns fully, but it helps. We talked about in college algebra that a common logarithm is one whose base is 10. We talked about in college algebra that a logarithm whose base is the natural number e is called a natural logarithm. That's what we're going to focus on in this section. We're going to differentiate and integrate things involving e to a power, e to the x, as well as natural log. So this is really the foundation for this section. And then you also learned in college algebra something called change of base, which honestly we don't necessarily need to apply in these examples that we'll do. So really the upshot of this, I want to remind you, is that e is actually a number in mathematics, 2.71828, blah, 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 blah. And so you have functions involving e to a power, and you have functions involving natural logarithm. In example 1, you will notice that all of these examples involve finding the derivative of e to a power. So, it is now time to introduce the calculus rules. Yeah! Calculus rules, man! Yeah! What are the calculus rules related to differentiating e to a power? Well, it turns out that this is probably one of the easiest derivative rules you'll ever learn. So, again, Roman numeral 1, if you have an exponential function, e to a power, if you apply the definition of derivative to this, the derivative of e to a power is e to that power. And that will be the rule we will use to do all of these examples on slide number 1. So the derivative of e to the x is e to the x. Now, you got to remember, though, that that's the foundation to it, but you also got to remember our good friend the chain rule, because that's, and all the other rules that we've learned in the past would still apply here. So, when somebody says find the derivative of that function, here's how it works, and you'll get the hang of this. See, the way I look at it would be that 4x plus 5 is kind of like inside the parentheses, so to speak. And so when we differentiate this, our brain would really need to think in terms of chain rule. And the 4x plus 5 would be the inner operation, and the e to that power would be the outer. So if you recall, I hope you recall, the chain rule, chain, would be to do the derivative rule associated with the outside operator first. So the idea would be that since that e is the external operator, we would apply this new rule first, e to that power. So the idea would be, remember how we leave that inside function alone when we do the chain rule? Okay, so the idea would be that the derivative rule for e to a power is e to that power. That takes care of the outside one. Then, remember our chain rule, friend? Then you multiply that by the derivative of what is inside the parentheses, so to speak, and the derivative of 4x plus 5 is 4. And this would be the derivative of the inside expression. So it's chain rule. And you plug this new e idea into the discussion as you do it. So when you have e to the power, basically it's going to be e to that power times the derivative of that power. That's the application of the chain rule when you see something like that. So let's just punch our way through and we'll review some of our old friends here. So here's our next function, f of x, and it is 3 times, notice this is e to a power again. So, okay, 3 is just a coefficient. You remember when we take derivatives, we just carry down our coefficients. That's nothing new for us. And then, much like the one above it, the general structure of this would be e to a power. And again, you could think of that power as being inside some parentheses. The point is, this is a chain rule scenario again, where we have an inside-outside situation. So the first bit of logic would be to go, well, the outside operator is e to a power, so our new friend, e to that power. Now remember, when you do the chain rule, you leave what's inside the parentheses, so to speak, alone. Let it be, let it be. All right? Yes, my singing has not improved. So that would be the derivative for e to that power. The derivative of e to a power is e to that power. But according to the chain rule, then we move inward and do the derivative of what's inside the parentheses, and that would be the expression 6x squared minus 7. Boom. Make sure you have your parentheses there. So again, this question, this example was very similar to the one above it. The only difference was we had a coefficient and our expression was a little more complicated. Not much, but that's the idea. So, what I'm trying to do with this would be not only to help you review or actually to learn this new rule, but also to review all our good old friends, all of our old derivative rule friends. So, again, you can hit pause anytime. Let's just keep punching along here. Now, I hope as you begin to write down this next one, and I don't know if you've been working these questions along with me like you would in class. I hope you have been. But I hope you're looking at that going, oh, that's a product rule situation, because we have two expressions that have variables in them, and they have multiplication between them, don't they? So I hope you're thinking product rule as the overarching theme of this one. So we get to review our good old friends, all those old derivative rule friends. And so here we go, right? Two factors, both have x in them. That's not just a coefficient. That's not just a 4. It's got a variable with it. So we've had that discussion before. So here we go, right? Ursula, Veronica, each factor gets a turn being a derivative. So my pattern that I like to use is to leave the first one alone and then take the derivative of this one. That's that e situation again, right? Chain, chain, chain. So you would say, well, e to a power is e to the power, and then the derivative of the power itself. So all that right there would be the derivative of that expression, wouldn't it? Awesome. Plus, now it's your turn. Well, that's easy. That's 12x squared. It's kind of hard to turn your brain back to derivatives again, isn't it? We've been doing integrals for so long, but just keep in mind, we're back to doing derivatives. And then you've already had a turn, second factor, so e to the x squared just carries down as is, and there it is. So that would be the product rule, and again, within the product rule, we got to enjoy our new rule, specifically the derivative of e to the power. E to the power, derivative of the power. That's basically what will happen every time on one of those. So there you go with that. All right, I might just do this first column and then hit pause. We'll come back and do the other column because my marker is dying on me. All right, so next example, f of x equals 5, blah, blah, blah. You see it here. See, this is actually testing our memories of our good old derivative rule friends. So I would hope when you looked at this one, you would say, well, if you're going to find the derivative of that, well, that's an inside expression with an outside power. That sure looks like chain rule to me. Chain, chain, chain. So you would say, well, okay, we'll do the power first. So that would be 2 and 2 minus 1. That's the power rule, isn't it? Because the outside operator was a power. And what do you do with this thing on the inside on that first go round? Yes, let it be. Let it be. You leave it alone. Chain rule. I know it's been a long time, but that's what that would be. So that creates that. And then in our minds, don't we somewhat cover up the 2 and go, okay, 2, you were a power, you were outside, we did your rule first, we're done with you. And then you look at the inside and you go, well, that's just terms. So you go through and do each term. All right, here we go, our new friend, our new rule today. So wouldn't this be coefficient 5, e to the power, derivative of the power itself. And yes, we could multiply the 3 with the 5 and make it 15. You know, as I've done all semester, when we introduce a new concept, I'm like, yeah, the cleanup will come later, all right? Although they're in much more later. Don't worry about cleaning them up, that's my point. Minus, okay, that term, coefficient, e to the power, derivative of the power, and that would close off that second expression. And wouldn't this be the derivative of the internal terms? And you guys have been very good about picking up on how to plug new rules in with the old friends we've had. So I hope that made sense. And okay, why don't we wrap it up on this one, and then we'll pause, and then we'll come and do the other column of e to a power examples. So, all right, let's make some room for this one. I hope, as I'm erasing, you're thinking, I know what that guy's going to do on that next one. He's going to rewrite it from the screen to the board, as in e to the negative x plus e to the x. Wait a minute, what happened to the radical? That guy's going to change it into an exponent, isn't he? That's right. And so wouldn't that be, let's see, doesn't that have a first power on it? Cube root, wouldn't that be 1/3 power? This is all stuff we've been doing for a long, long time. Got to be a snob. That's just stuff, that's just algebra rewrite. Okay. And then I would say this has similar structure to the one down here in terms of, notice by the way, prime means, hey, I'm ready to do a derivative now. Aren't you? And you hopefully would realize, just like the one underneath, that we have an outside operator, right? Power on a quantity, chain. So we employ the power rule first, 1/3 and 1/3 minus 1, which is negative 2/3. Leave it alone. Let it be. Let it be. All right. And then you do the derivative of the inside expression, which is terms. And so the derivative of e to the negative x would be e to the negative x times the derivative of negative x, which is negative 1. I could either put a negative sign in front of that, or I could put in parentheses negative 1. Either way. Plus, and then e to the x would be e to the x times the derivative of x, which is just 1. And indeed, you wouldn't have to put the times 1 on the end of that, and that would be the derivative, this would be the derivative of that inside. So it's chain rule, and this new e thing, and I am showing this to you as I've shown it to many people before you, and they understood it, so I have very little doubt that you're going to understand it. So we're going to clear off the board a little bit, and we'll come back and do that other column, but pretty much it's just more practice. All right, let's pause.